What is old math nerds? In this video we're going to talk about exponential growth. First of all, algebraically, a function that has exponential growth is going to look something like this. F of x equals some c, some constant c, times some constant b. Let me write that thing a little nicer. So b raised to the kx. Okay? And that's going to be our general form for exponential growth. For when we're talking about exponential growth, for example, for populations, population growth, it's going to look like, let's say, p of x equals, well, let me change that. A lot of times, instead of using the variable x, when you're talking about population growth, it's with respect to time. So it's going to equal, this c here is going to be your initial population, and a lot of times you'll call that p naught, and then times, let's say if it's in that b, for example, if you're given your population growth is doubling or tripling or something, that would, let's say for example here that we're doubling ever so often, so it's going to be 2 to the kt. Okay. Now, exponential growth itself, I really encourage you to get out your calculators, and for growth also, let me say that b, that thing b must be bigger than 1. Okay, to get exponential growth. Since we're talking about growth here, we know that b is bigger than 1. And I really encourage you to get out your calculators and graph a few to see what the graph of these functions look like. That is, for example, f of x equals 2 times 3 to the 5x. Alright? Get a calculator and graph them, and you'll see, I mean, they all have a very similar shape. And to see why, so for example, when here when x is 0, f of 0 is going to equal 2, because when you put the 0 in for x, you get 3 to the 0, which equals 1. And so that's why this, in the population growth, that p naught gives you your initial condition. So so let's say that there's 2, and then after you get your initial condition, they're all going to look something like that. Exponential functions get big fast. That's why you always hear people say things are growing exponentially. That's really saying they get big fast. Exponential growth is, over time, things get really big. Okay? And when we model things with exponential growth, it only works in a small period of time, because if you let it, if you try to model it as x or t goes to infinity, this thing is always going to blow up to infinity eventually. Okay? It only works in small periods of time. Let me jump to an example. Here we have a colony of bacteria that has 700 cells. So that's going to be my p naught there. That's my initial condition. 700 cells at 1 p.m. These bacteria reproduce at a rate that leads to doubling. And let me do that in green. Doubling every 3 hours. How many bacteria cells will be in the petri dish at 9 p.m. on the same day? Okay, now you have to use your brain here and think. Not just try to plug into formulas. I mean, you really want to think about these things. So we have this thing is doubling every 3 hours. That is, we're multiplying. That is, we have some initial condition. Let me go over here to the right. Let's sketch a little bit. We have some initial condition, p naught. We want it to double in 3 hours. That is, I want to multiply it by 2. That's how something doubles in 3 hours. So if I just put a t up here for time, then that thing, when t equals 1, that thing is going to double. So I need it to double every 3 hours. So what do I need to put, how am I going to make this thing, this P naught, double every 3 hours? Okay, so if we know that we need it to double, we know that that exponent has to go up there. We need, in 3 hours, we need that thing. We need this to be a 1. That is, I need P naught times 2 to the in 3 hours. So what's it going to be? 1/3 T. That is when T is 3. So T equals 3 implies P naught times 2 to the 1/3 times 3. And you see there, that's going to give me, which equals P naught times, oops, got so much stuff going on here. It gives me P naught times 2 to the 1/3 times 3 is 1, and we see that that's going to make it double in 3 hours. If it was going to double in 4 hours, that would need to be a 4 down there instead of a 3. Okay? So let's get the formula for it. So we're going to say P of T, and this was just scratch work over here. This was a scratch work on the side there. That was me figuring things out before I actually wanted to write a nice looking problem. Okay, so P of T P of T equals my initial condition 700 times, I want it to double in 3 hours, so 2 to the 1/3 T. Alright, and note my initial condition, if I let T be 0, 2 to the 0 is 1, so I get, at time 0, I do get 700. So how many cells will be in the Petri dish at 9 p.m.? What is that, 8 hours later? So that's going to be P of 8 equals 700 times 2 to the 1/3 times 8, which is going to give me that P of 8 equals 700 times 2 to the what, 8/3. And let's see, I'm going to say that's approximately equal to, let's break the calculator out, 700 times 2 raised to the 8/3. Make sure when you're putting fractions and things in these exponents that you use your parentheses. 8 divided by 3. Alright, about 4445, we'll say, because this is just going to be an approximation. So approximately 4445. So 4,445 cells in the Petri dish. Okay, let's see how we're looking on time. We got a couple minutes. That's going to be a, let's see. Nah, I don't want to rush through this one. Let me stop here, and I will knock this problem out in the next video and maybe another one. Okay?